Welcome to another podcast. This episode, we're going to be taking a look at a very important principle involved with the theory of Laplace transforms and how they interact with linear differential equations. In particular, suppose that I was looking to solve the equation ax double prime plus bx prime plus cx equals f of t. And let's suppose, just to simplify this a little bit, that the initial conditions here were x of 0 equals 0 and x prime of 0 equal to 0, so that these conditions, these are called rest conditions. So there's initially no motion in the system. Now, in order to solve this, if I was to take the Laplace transform here, the fact that these conditions are at rest is simply going to make this a pretty easy process. All I have to do is basically copy down, so taking the Laplace transform of both sides, basically copy down the characteristic equation. So as we've talked about in class, the characteristic equation shows up always when you do the transform. And so we would have this for both sides. And so finally, if we were to solve for the transform variable, we would get that it's f of s divided by the characteristic polynomial. Now, in particular, I want to think of this as being f of s times 1 over the characteristic polynomial p of s. And these things have names. This guy right here is called the transfer function. And so you will typically see this in a lot of books written in the form f of s times w of s. So the w of s here is 1 over p of s. That's the transfer function. And so if I was to look at the inverse transform, so we're going to take the inverse transform now, then the transform variable x of s becomes x of t, and we have a convolution situation here. So I'm asking, what is the inverse transform of f of s ws? Well, that's just the inverse transform of f of s convolved with the inverse transform of w of s, which is f of t convolved with w of t. Now the question is, what is w of t? Well, w of t is called the weight function. Most textbooks will call it the weight function. It sort of gives the weight of the system to the whole process here. And so this is really cool. It gives us a solution for the differential equation based entirely off of only knowing the characteristic equation. That's all I need to know to be able to do this. So let's just do a small example of this. So my example of this is, let's look at x double prime plus 6x prime plus 10x equals f of t, and I'm just going to leave f of t as f of t. And we're going to do this one at rest to start with. So how would I solve that? Well, if you take a look at what we ended up with as our answer here, this process, which is called Duhamel's principle, Duhamel's principle says that the solution is nothing more than x of t is equal to f of t times the weight function. And the weight function here is the inverse transform of 1 over the characteristic polynomial, which is s squared plus 6s plus 10. And so what we should recognize here is that this factors, or actually, excuse me, it doesn't factor, but if we do completing the square, remember the way completing the square works, we can take s squared plus 6s plus 10. You take the middle term, divide it by 2, and then square it. So 6 divided by 2 is 3, and then if you square 3, you get 9. So what you do is you add in 9, and then you take the 10 that was there and subtract 9 from that, so nothing's changed. And then this part here is the perfect square, s plus 3, and then 10 minus 9 is 1. So I can look at this as s plus 3 squared plus 1, and hopefully I recognize that inverse transform. It turns out I do. That is the inverse transform of e to the negative 3t times sine of t. And so it turns out that the answer to this problem is simply this particular convolution. And so that's a really good result that we have there, but it turns out we can actually take it further. All right, so at this point, I want to add a little bit more to this to talk about specifically the w of t. So where does w of t come from? Well, it turns out that w of t is the solution to this differential equation. So if we looked at ax double prime plus bx prime plus cx equals the delta function, and then we had initial conditions at rest for that problem, then what we would end up with in this case is essentially a problem where you would have the transfer function being the only thing that shows up in the problem, because remember the transform of the delta function's 1. So if you think back to what we did over here, how would that look differently? We would just have x of s is equal to the Laplace transform of the delta function over the characteristic polynomial, which would just be 1 over the characteristic polynomial, which is our capital W of s, the transfer function. And so the solution to this equation is the transfer function, or excuse me, is the weight function. So the weight function solves that equation, because you can see here that x of t would just be w of t at that point. The book, or lots of books, not just our book, but lots of books will either call it w of t the weight function. Some books will say that x of t is equal to e of t, where e of t is the unit impulse response. And so depending on which book you have, which notations you have, you might see either of those. But the point is that the weight function is the solution to the delta forced equation. And that's especially important to know here, that's what's going on with the weight function. And what's even more impressive about all of this is there's no need, in order to calculate the solution to these differential equations, there's no need to know what the input is. I don't know what f is at any point here. And in fact, I don't even need to know to calculate the weight function. I don't need to know the initial conditions, because the initial conditions are zeroed out. If the initial conditions aren't zeroed out, that's going to add a little bit more complexity, but that's actually very easy to calculate. And it turns out that calculating that is actually dependent upon the derivative of the weight function. So if we were to go a little bit further with this topic, in fact your book does, we could give a full solution for any set of initial conditions based off the derivative of the weight function as well, or the input, or the unit impulse response function. So this is the sort of the basis for being able to solve these differential equations very quickly, very efficiently, and testing, and here's where it really comes into play, testing multiple right-hand sides. So as an engineer, you might be interested, you might have a system, and you want to figure out how it responds to multiple inputs to know if any resonance occurs. And rather than having to solve the problem for each and every input and expecting a different answer, what you learn is that it doesn't depend on the input at all. So you can use the same model multiple times with the input and just test the response to the inputs and know everything there is to know about the original system. That's a very handy thing, because it limits the amount of calculations that you have to do in order to actually come up with an answer. All right, thank you for watching.